We're back with a real consolidating effort today. We're going to be looking at perpendicular bisectors, which is highlighted there. I've already advertised in class a couple times. This is going to be a slightly longer one, but you will find in the coming minutes that I'm going to actually present model solutions to the questions of this particular homework set 4H. When this is done, we will be truly ready to embark on sort of the crowning achievement of this chapter, which is the Voronoi Diagrams. So without further ado, let's continue on and we'll see where this takes us. All right, the first thing is a perpendicular bisector. I think we should know what it is. If you've got a line segment, like for example the one there, denoted with the letters S and H, we're trying to find kind of like a border line that goes directly between them on a pathway that's perpendicular to the one that joins them themselves, and it splits them perfectly in half. Now this lends itself really well to the Cartesian plane because we have coordinates. We can bring our formulas in for different things like lengths and midpoints and equations of lines and stuff. And the application to this is really quite fascinating. And there's also something that you can do in the world of geometry is rather interesting, I think, as well. So anyway, let's just take a look at that. So in this case, the line segment marked with the letters F and I is the perpendicular bisector to the line that joins S to H. I'm going to show you how the calculator can actually make a perpendicular bisector. We're going to go to the geometry page. I'm just going to come up with a line segment here. So we go to the points and lines submenu, and I'm going to look for a line segment, which we're going to just pop a point down, 1, and another point down somewhere else, 2. Now remember, escape. You got to hit escape to get out of that mode. Otherwise, it's going to start making more line segments for you. And I can move that line by adjusting one of the points, pick it up, move it around. Grasp it. I could grab the whole line and move it around if I wanted to. But what I'm going to do is do a construction here. Construction is when we build something against something else that already exists. Perpendicular bisector, there it is. So I'm going to say it has to be the perpendicular bisector from A to B. So I click on both those points and it draws the line down. So that line, although unnamed, it didn't give any letters like F and I like in the previous graphic, it is the perpendicular bisector. As I move these points around, that line will remain perpendicular, and it will continue to split the distance between A and B perfectly in half. That's what a perpendicular bisector is. Let's continue then. Move it along here. Oh. All right, so here now that's basically it. All we need to do is practice this idea. It sounds like what happened to the long video. Here it comes. Here's the different questions of section 4H. And we're going to be dealing with, all of them. I foolishly put down 1, 2, 3, and 5 as a demo. That was always planned to be a demo, but I'm going to do 1, 2, 3, 4, and 5. So settle in here, get your calculator out, hit pause frequently and see that you can follow along and learn where the calculator stores these valuable commands to sort of navigate these questions. Two friends, Allison and Bernard, are walking along two different roads. The roads can be represented along the lines y equals negative y. You can read it for yourself. Allison's on the first road at a point with the coordinates 0, 4, 10, and Bernard is on those coordinates there, 50, negative 75. Verify that Bernard is on the road with the equation. Now, I'm just going to go back. I didn't video demo this. This is just some of the things we've done before. In both of those cases, those lines are presented as y equals, and that's called function form. So I can go ahead and just pop them down. There's a function 1 in blue and function 2 in red. You can associate those with these equations back over here to know which is which with Allison and Bernard. This is you want to verify that Allison is at point 4, 0, 4, 10. Well, that's an x-intercept. Oh, sorry, it's a y-intercept because the x value is 0. And that's going to be the value over here, but I'll just check that out. And what else can we do here? We want to verify. So the other thing you do is you can pop in the value. If I put in the value 50 into this second equation, which is diagrammed in red, I can compute that the corresponding y value is negative 75, which is here. And that's confirmation that this point, 50, negative 75, is on the red line somewhere. I can go ahead and locate those points using various techniques. When the x value is known, it's a trace. And you could do the same here, trace. And of course, there's the intersection, which we've already seen before. So let's find the coordinates of the intersection, and that's 340 and 70. If you need help with that, ask me. Happy to come over and give you some guidance about where to find that. Okay, find the equation. Here we go now. The equation of the perpendicular bisector. So now we're actually going to split 2 points in half, the distance in half, and we're going to run a line perpendicularly between them. And then I'll deal with the rest of the equation later on. I've made a little embedded video for this one. First thing I'm going to do is I'm going to make the line that joins 2, 2, and 4, 6. Equation, geometry. In the points and lines submenu. And I'm going to I'll go with a line segment this time. This means it starts and stops at those points. I don't need to have it going on forever in both directions. Open a set of brackets. I already did 2, 2. There's 4, 6. And there's the line. All right, escape the mode. And that's it. Now I need to have a line perpendicular to that and splitting it in half. Down to the geometry submenu. This is in the construction area. And we're looking for a perpendicular bisector. And you just either click the line or click the 2 points at its end. Click, and there you go. And that is the perpendicular bisector. That line splits it. If I want to come up with this equation, click it, and there it is. -1/2 x plus 5.5. So we've already accomplished the first bit. Find the equation of the perpendicular bisector of the line segment, blah, blah, blah. Okay, next question. It says the equation of the line passing through CD. Oh, by the way, this still goes back to the previous one. Difference in the x values, difference in the y values. I could have found that the slope between A and B was 2, so therefore the perpendicular slope, and I find the midpoint is 3, 4. So effectively, what I'm doing now is I'm trying to find the equation of a line that has slope -1/2, because that's the perpendicular 1 to 2. Notice that 2 times -1/2 has a product of -1, which is what we want for perpendicular, and we're trying to make sure that that point includes 3, 4. Why is it 3, 4? Because it's the midpoint, and that goes back to the first topic of this chapter. And you can see now that the line must be y equals -1/2 x. That's the slope we want, and the b value is unknown, so I substitute the values in for y and x. And I just use my calculator to solve for it, and it's 5.5. And you can see that that exactly matches what we had previously. It was -1/2 x plus 5.5. So it's all good. This next one here, we're talking about the line that, there's a line that goes through a point C and a point D, although we don't know their coordinates. And they're both on the line x plus y is 3. So I went ahead and I graphed that using standard form. It's a graph equation template for ax plus by equals a number. I typed it in there. It said that the equation of the line passing through C and D is this. Right, that goes through C and D. And the midpoint of C and D is 2, 1. So that's got to be the middle right there. Wait a second, did I finish that? Maybe I didn't finish that question. Let me just go back and check. Yeah, so if 2, 1 is the midpoint, that's all we really need. We don't need the point C and D. And perpendicular to x plus y is going to be a line that's got a gradient of 1. This one's got a gradient of -1. You could rearrange the terms to find that, and that would be it right there, using the slope point format. If you need help with that or some more algebraic detail, let me know. All right, moving along here. Number 3, find the shortest distance from a hotel located at 2, 4 to a straight road with that equation. All right, let's see. First off, I'm going to take that equation of the line. That's a road. And I'm going to redesign it the way that the TI calculator likes that information to be received. And that is 3x plus 5y equals a number. In this case, that number is -8, because this 8 is going to make the journey to the other side of the equation. When I plot that down, I get that, and I can see the point 2, 4 is here. Now, the shortest distance between a point and a line must be one that travels perpendicularly toward it. Notice that if I go in at any other angle toward the line to greet it, I would get there, but it's a longer journey. The shortest journey is one that goes directly perpendicularly toward it. So in essence, what I'm trying to find is the point on this line here that perpendicularly connects to 2, 4. How do we do that? Well, I'm going to have to figure out the gradient of this blue line. I'm going to do that by isolating y. I've moved the 3x and the 8 to the other side, giving me this line here, 5y equals -3x minus 8. And then I'm going to divide both sides by 5 in order to ensure that y is isolated. So it's -3/5 is the gradient of that line or slope of that line. So if I know that I need a line that's perpendicular to it, it must have the gradient must be perpendicular, which is to say the negative reciprocal, or what number multiplies with negative 3/5 to provide an answer of -1, and that was covered in our last lesson. So that number is 5/3. It's always the reciprocal of a fraction, and change the sign. So now our problem has really evolved quite a bit. I'm now looking for the equation of a line that has got this slope 5/3 and it goes through that point there. Well, that seems rather tailor-made for this slope point form of a line. I enter in the point that I want, 2 and 4, 2 for the x, 4 for the y, slope is there, rearrange the terms, and I can go ahead and graph that line, and there it is right there. And it certainly appears to be perpendicular. So if I want to know the point on the road that's closest to 2, 4, that means it must be the point where those two intersect each other. So now I'll go back and I'll invite those two in, and I'll ask my calculator through the analyze graph mode, and I'll surround the point and find the intersection. And it's the intersection point is -1, -1. And now they want to know what actually is the distance. Well, that's using the distance formula. What is the distance between -1, -1, and 2, 4? So we use the distance formula to get that. There's the distance formula between 2 points in 2 space. I put the x values down, 2 and -1, the y values, 4 and -1. Find their differences, add their squares, and the answer is approximately 5.83. That's the closest that 2, 4 ever gets to the blue line shown there. Two towns are located at the points A and B, and a school is to be built on a road. So it has to be on the road. I can understand that. But you want it to be the same distance from A and B. So let's take a look at how we do that using technology. First things first, I want to see where these towns are and where they're. So I'm going to put points down. Use the coordinate option here. Just type in 2, enter, -2, enter, and open up another one here. Open up a set of brackets, 8, enter, 5, and there it is. So that means those are the points. That's where the two towns are. Now we're going to build a school. That's going to be the same distance from those two different towns. But it also has to be on a road whose equation was given to us. So that road equation is already presented in standard form. So I'm going to use the standard form entry option, which is, no, I'm not doing that. Back up. Oh, I'll find the perpendicular bisector first between those 2 points. So it's going to be between these two guys. And that's the line that is, every point on that line is the same distance from each of those two. So if I now go find the equation of that line, there it is. Not particularly helpful numbers, but you know, I've seen worse. Now we also know that not only does the school have to be on that line, because it's all the points on that line are the same distance from A as they are from B, it also has to be on the road. And the road was given as -x, -1x, coefficient of y is 7, and the constant is -4. Hit enter. And there it is. So the school pretty clearly has to be at the intersection. And that ensures that it's the same distance from A as it is from B. And it's also on the road, which is labeled -x plus 7y equals -4 and shown in blue. Want to find the intersection of those guys. Means I have to actually type in the coordinates, the equation of the other line, because it's only like a temporary storage. It's not, doesn't really recognize it. Let's get to remove that now. And that's the perpendicular bisector, redrawn, rewritten. And so now I can go ahead and find the intersection of those two lines. Here we go. Intersection, surround it, and let it get labeled. And there it is. So at the coordinates 6.34 and 0.335 is exactly where the school has to go to meet the criteria of the question. Okay, and our last question of the homework set deals with now this is really getting very close to Voronoi diagrams. Imagine that you've got a park, and the vertices at the corners of the park, a triangular park, is -1, -1, 4, 4, and 7, -1. Some town planner has decided to erect a fountain in this park, and it has to be the same distance from all vertices. Right. We need to have a little refresher about what it is to be equidistant. If I said I've got a single point and I'm going to draw all the points in the world that are the same distance from it, I would be tracing out a circle. If I was to ask you to, outstretch your arm, as far as it can, and delineate that distance around the core of your body, you'd spin around and make a circle around yourself, and all of those points would be just as far from where you are as any other point. So what happens if I've got three? If I've got three of them, you are actually going to be delineating out what we call the circumcircle, and that is a circle that surrounds 3 points. The center of the circle, it becomes our next investigation. How do we find the center of a circle doing that? Well, it turns out that triangles, depending on your criteria, there's almost countless number of circle options. If you wanted to have a centroid, which is like the center of gravity, so you could balance a circle, you would join the midpoints of the 3 sides together and they would meet at some place. There's other ones here. Incircle is when you can draw a circle that just fits in the 3 sides of it. And then we've also got this one here called the circumcircle, and its center is called the circumcenter, and that means it's a circle that neatly surrounds, just barely surrounds a triangle. And in order to do it, it must actually go through all 3 vertices or corners of that triangle. Interestingly, the way we find that center, it's where the 3 perpendicular bisectors meet. The 3 perpendicular bisectors of the 3 sides of the triangle. Our advantage here is that we have technology to do that for us. And here's how we're going to do it. So there's our circumcenter surrounding a circumcircle surrounding a circumcenter, and this circle passes through the 3 vertices. So that means from the position of this blue dot, since these points are on a circle, they're all exactly the same distance away from it. And that would satisfy the condition of this question, and it will be something that we're going to be doing heavily when we do in the Voronoi diagram. So you find this circumcenter by finding the perpendicular bisectors, and you find out where they meet. And all 3 will always meet at the same place, which is really quite fascinating. So I've started by taking 3 points. There they are. This is just randomly 3, but this isn't those particular ones. And I found the sides of the triangle. Oh, by the way, if all 3 perpendicular bisectors meet at the same place, then that means any 2 of them would meet at that same place as well. So it's a bit redundant to find all 3. You can just find 2. You know the third one would go there as well. So I'm just going to find 2. Then once I find the 2 lengths of the triangle, I look at their individual perpendicular bisectors, which I've done, and I can see where they cross, and I'll highlight that point right there. That's where they cross. That is the circumcenter of the circle that will go through the 3 points of the triangle. And if that's the case, then those 3 lines I've just added must each be versions of the radius. I can start removing some of these extra pieces here that I don't need. And that means there's a circle that goes to that center red point, and it connects the 3 outer points. And now I'm going to go ahead and do it for this particular question that we've been looking at. I'm going to plot the points -1, 4, 4, and 7, -1. Pop them all down. I'll make I guess I'll go with a line segment this time. And open up a set of brackets. -1, -1. Pop it down. I'm still in the mode. I can just keep going. Bracket, 4, enter, 4, enter. And I'll do one. Oh, now I'm going to go to the point. One more. 7, -1. Open up a set of brackets here. 7, -1. Now, if I want to go back to a point I've already found, I can just hover over it and it will say, do you mean this point? Point B? Yes. Click. And do I want to go to make A and C? Sure, why not? So I'll go a line segment from here to here. Click. And now I'm going to hit escape because I don't want to be making any more line segments. And that's our triangle. Now, to find their perpendicular bisectors, all I got to do is say, well, it's perpendicular bisectors, go to the menu, geometry, I'm going to make a construction, build something, which is a perpendicular bisector, and I just got to name the lines. The one that goes from A to B, there's its perpendicular bisector. I'm still in the same mode, so I can just keep on clicking points. One from C to B, Oh, C to A first. Yeah, I can already see where the center is going to be. It's right there. But I'll just do the last one too, just to make sure. And sure enough, all three connect. That means that point right there, which appears to be, I don't know, what is that? 4-0? No, 3-0? Is the center of it's the circumcenter of the triangle. Right, so I'm going to make a circle now. Shapes. I'm going to make a circle. In this operation, what you do is you place your cursor where you want the center to be and click it, and then you drag out until you get the right circle that you want. And there it is. There. So that's the circle that joins up all 3 points, and the center of the circle must be the circumcenter, which is on the x-axis there. I hope that makes sense. So where does it have to go? You would just go to that point there. That's 0.5. It's 1, 2, 3. If you wanted to find the intersection, you could do that using the calculator to find the intersection of a couple lines. And there it is. Find the location of the fountain, which we've done. So we're back. 4H is now completed. I did 1, 2, 3, 4, and 5. That's the end of it. What you should be doing with the rest of your time is completing anything that's not done. I think 4G is presenting, it's a longer exercise set than many of us maybe thought it would be going into it. You probably have some work left to do in 4G. And if you don't, you can start thinking about your IA topics coming up, or whatever you want to do really. But basically, we have completed that. We're going to come back next time and looking at putting all of these ideas together and exploring Voronoi diagrams. Fascinating stuff. Okay, have a good day.